Okay, we're ready for our next talk here. We're going to switch gears a little bit, and Jean is going to switch us to 3D printers and CNC machines. So, thanks, Jean. Welcome.
Hey. Hello. Thank you for being there. We try to talk about something a bit different. It's not about kernel and so on, although it is what I do all the time, but I wanted something a bit different, and let's see. Who am I? So I'm Jean. I'm a freelance running neworbits.com, doing low-level stuff, bootloaders, hardware, software, Linux kernel, optimizations, all those. I have collaboration with Mind, Mind.be in Belgium, so we are working together on those projects, internal projects and also customer projects. It's a great collaboration for years. And so, as you can see in the box, what I do is work on a lot of hot topics that we are discussing at this conference, like SBOM, right? Fast boot, secure boot on various platforms, optimization of resources, of boot time, all of those. That's what I do all day long for customers. But this is more of a side project. This is more of, I like to tinker with machines, use open source software the best I can. And this is about my findings and how I do stuff. But I really would like you, if you have more info, more use cases, more usage, this presentation is a living presentation. So if you have suggestions, I can change that for the next talk, right? Next conference, let's see. All right, so it's about using open source all the way. It means from A to Z, hardware, software on the machine, but also, more importantly, software on the host machine. So you have your laptop, you want to create a model, you want to print it, you want to CNC a part. I want it to be fully open source. So I will try to give a round trip on the best software we can use, open source, of course. And I will show you how it's done. And if time allows, I have a bit of a demo on Freecad. Freecad is the CAD software on the host. So what are the needs? I would say for 3D printing, it's really common. So everybody knows that. It's really stable, really robust. You can print 24/7, no problem. This is not an issue. But you need to find the correct tools to do it. On the other hand, CNC is a different beast. So it's much less common. It's more industrial. And the goal is to do simple CNC, three-axis, rather manual. So when you have to change the tools yourself, you add all by hand, let's say. It's a light CNC that you could even use in small business cases. If you do panels for automation, you do plexiglass like this thing, you could CNC that kind of stuff, no problem. But it's not industrial, it's not Formula One part, you know, that you need a 5-axis machine and micron precision. It's not the same world. This is light CNC, but still really robust, really workable for everyday use. Right, starting point. I started all of this because I could put my hands on a machine that I got for free, but it was really obsolete and not doing what I wanted. So I say, why not do it the right way and do it fully open source from scratch? And this talk is about, I will show you the case of 3D printing first, because it's much more common. And I will try to use all those principles to do CNC. That's a bit what I want to show. Quickly, a bit of history of 3D printing. You see there the very first 3D printer that can replicate itself, 2005. So it originally wooden stuff, threaded bars and all, bolts, screws. That is meant to be, you can do that at home and you can replicate the machine so you can make it better. So all those wooden things you can replace by a part that the printer prints itself, for itself and for the next. Scary, right? Then came more. The hardware went better, of course, but software started to pick up. That's really important. So 2010, Prusa started with a machine that is really inspired by the one you see in the picture. Then came Ultimaker and so on, firmware for the machine, printing farms, and all. So a word about open source. So what is open source in this case? It's not only software, it's the whole chain. So it's electronics, you know, the hardware, the schematics, the parts that you can find even. The extruder on the machine is really a part that is custom made to extrude the material. The heater, all of those hardware parts, they must be open source as well. We need to find schematics for them, resources for them. Obviously, also you need the firmware. Firmware on the machine needs to be open source. That's pretty basic. Yeah? It's pure software that you compile and flash on the board. The host tools need to be open source. If you want to do it fully, you take a Linux machine and you install purely open source kernel and software on it. You are safe, you are good. Although most of the host tools, they can run on Windows and Mac as well. It's really flexible that way. About the slicers, for instance, the one that slices your model in layers to be able to print them. We have an history there, and for instance, you see slice 3R. Slice 3R is the first one that was there, was merged and evolved into the Prusa slicer that we have today. It's fully open source. Ultimaker is making one, Cura. And then you have Octoprint, really the thing that you put on the machine, the laptop to control and monitor your print. And also important, the models. So you need models to get inspiration from or to print. You can find them on printables.com from Prusa. Thingiverse is there as well. That's a bit of it. So open source needs to be from A to Z, the whole chain. So now 3D printing. What do you need as host tools? See my mouse? Not really. Oh, yes. All right, so in blue, then you see you need a model. So what do? You have a CAD application that you can create model from a 2D bitmap, 2D drawing, or from purely 3D modeling. The thing is, you get a part really on your computer. What you do then is you slice this in layers of a given size. There are a lot of parameters, of course. And for every layer, you generate G-code. G-code is machine code. Just is basically text, a line telling, please go to this location, X, Y, Z, with that speed. Please draw an arc, so a round trajectory. Please do this, please do that, please enable, please eat at that temperature, and so on. That's the G-code. So you really need the slicer to generate the G-code from the part you have. And then the G-code you send to the machine, so the yellow part below the line, it's the machine, 3D printer, right? Or you do it the old way, the old-fashioned way. You put the G-code on a SD card, you insert the SD card in the machine, and you do print. And it starts to, every G-code makes it move, and so on and so on. So you print, that's fine. You have an LCD, a basic two-line LCD, something really basic with buttons, and then you can control a little bit what you do, change the filament, reset it, whatever. And then the new way that you can use, it's really interesting, the green part is the controlling part. So on the laptop or Raspberry Pi, you put Octoprint, for instance, and you can monitor the whole thing remotely. So you can start a print and go upstairs, take a coffee, and look on the smartphone. You see the progression and the temperature and everything needed. You can control the print from there. That's quite convenient. Right, that's an overview of the tools. Now I will give you a rapid tour of those, what they are as open source. It's really important. Open source, I will not mention, not open source tools, which could be really good, of course, but this is not the point. 2D, basic 2D stuff. Vectorized bitmap is quite interesting. You can take a picture, vectorize, you will get a part that will neatly be imported into the 3D CAD program. As CAD, first Blender. Blender is not really a CAD tool. It's more animation, to do movies or small sequences. But it can be interesting because it has a lot of features, a lot of plugins, a lot of stuff. I use it sometimes to generate specific shapes or to deform a shape. That's quite nice. But be careful, it's not a real CAD program, so it will destruct geometry. So, for instance, you take two 3D parts, you do a Boolean operation, like intersect them, you will get the result. It's fine. But the two parts, the original part, they will be destroyed in the process, which you can accept in some case, but a real CAD program doesn't do that. It keeps the whole history. So if you change something in the original part, it will not be destroyed, but it will apply the whole chain up to the result. So I mentioned Blender because it has features that can be interesting. Next one, OpenSCAD. OpenSCAD is a script-based generation. So if you want to generate parametric parts, repetitive parts, that's really nice because you write like to do a gear. You can specify the number of teeth, the height, the length, the whatever, and it will generate. It's really a script. So it's quite nice. There are a lot of libraries available to do a screw, for instance, to do a bolt, to do a gear, whatever, you can do it. Right? Next one, Freecad. The one I like, this talk is about mostly Freecad because I think today this is a one-stop shop. I mean, with only this one, you can do everything you need. You can do 2D sketch, you can do 3D parts, you can do an assembly of parts to make a product, whatever. It's fully scriptable in Python, so you can automate a lot of stuff there. And today it's really mature, so from 0.19, 0.20, it's really usable. I mean, you can use it, no problem, works. Doesn't crash like every 10 minutes, it's really mature. It's coming great. 1.0 is really good now, and it's quite recent. And then you can see the CAM. One module is CAM, or what a part it was before. Now it's CAM. This is the module that allows you to do CNC. We'll see that in the second section, of course. So with one tool like Freecad, you can do really everything you need. Right? Now the slicer. Slicer is converting the 3D model to G-code. Two big ones, open source, Prusa Slicer and Intimate Cura, they are quite comparable. There are pictures of that. A lot of options. You can specify a lot of parameters for the printer you use, for the filament you use, for the model you are printing, and you can save that, export, share on GitHub, whatever. It's really, really good. It does a lot. And then there are exotic slicers. There are really slicers that you can use for a specific need. Like you see the picture right there, you can print things upside down at an angle without needing support. Because normally if you print part and then it comes bigger at the top, you need some support below it to support what you're going to print. Otherwise you print filament in the air. It will mess up, you will get a nice spaghetti plate of plastic. Not good. So this one can do different stuff. There are infinite Z as well. So if you want to print a part that is 10 meter high, you need a 10 meter printer, right? No. With this, you can print the thing at an angle and put the part on a sliding, a rubber band, like you see in the airport for your luggage. You can print that in angle and then advance the part every time. You can get a really long part. That's one of the examples. There are a lot of them. I mentioned two of them, but there are a lot. They are experimental mostly, but working. Now the control part, what's the green part? It's really nice to do the setup and maintenance. So what if you need to load new filament in the machine? What if you want to tweak temperatures and all, and then see graphs and so on? You can see the picture. You can control the whole thing there. On the left side, you also can upload the G-code directly to it. So drag and drop from your machine. You drag the file. You see there G-code in red. You just upload that. You do print. That's it. And then you get a nice camera view. You can do time lapse. You can do videos. Whatever. Right, so two type of control applications. It's mostly linked to the firmware you use. So the usual way, it's to have Marlin as a firmware, we'll see in a minute. And the control in that case is Octoprint. Octoprint is really nice, maintained by one person, the same since the start, so it's really worth mentioning, I guess. The other one is if you have Clipper as the firmware, then you have Mainsail or Fluid UI applications on the smartphone or on the laptop. It's really, really cool, really nice looking, and a lot of features, a lot of plugins. You can do a lot of stuff there, you can see. For instance, you can do a time lapse that every time a layer is started, it will take a picture. Every time, so the head is like on the side. So when you play the movie, you don't see the head moving. The head is always at the start, and it does. Cool, right? Next point, firmware. That's what runs on the machine itself. We have today two big families, two big software. First is Marlin. Marlin is the old one, the first one that evolved a lot. It's really stable, supports a lot of printers. But it performs all the tasks in one firmware. So it does the real-time tasks. There is no OS, but it's really like a really bare metal thing on Arduino. So it's moving the head, looking at temperature, whatever. But it's also doing the UI with the LCD. It's doing a lot. So it's maybe less performant, but it does the job. You can print 24/7, no problem there. Then the new stuff that it runs really well as well is Clipper. Clipper divides the firmware stack in two parts. One is the RT task, as I say, on the board, and the other runs on a Raspberry or on a PC and does the whole thing, all the rest, basically. I will show you there a graph. So on the left, you have Marlin. You can see Octoprint does the web server to do the control, the code, everything, and sends the G-code to the printer. And then Marlin does the whole thing. It interprets the G-code, moves the motor, everything. It does the UI with LCD buttons. And when I say G-code handling, you have to understand that when you draw an arc, for instance, it's only one G-code. But in the firmware, there is a lot to do. You need to interpret every tiny movement, make the head move a little bit, and be still real time, because otherwise the arc will be like not round, right? So that's a limitation of the thing. On the right side, you have Clipper. Clipper implements all the real-time tasks on only that on the machine, and then does all the rest on a different board. You can see it could even slice the model for you. It could even integrate the slicer. That's the new direction that new printers take. So they are even bought with an ARM-based or Arduino-based processor for the RT task, and then there is a main processor for all the rest, all in one board, quite convenient in the machine. Right? That was about the firmware. Now the machine. So when you buy a machine, it's like on the left. Nice marketing picture, right? It's so good and it works, no problem. But in reality, what you end up is what is on the right. We've added a lot of stuff there. So there are only 4 power supplies, an heated bed, so that you can print different materials. There is a Raspberry Pi on the side with Octoprint and a camera, and so on and so on. Optimized airflow, that's really important. You need a good duct tape to do that. You can see the blue at the bottom. It's the optimized airflow. But yeah, that's really fun. You can hack the machine as much as you want. You hack it, you try, and there is even a door you see in cardboard, whatever. Quite nice. But then you say, okay, but what about my firmware? I will be hacking my machine like crazy, but is it supported? Yes, it is. What we did on this machine has been hacked for robustness, speed, print size. The Z-axis has been modified so that we can print bigger parts, for instance. Higher temperature, multi-material, so we can print PC or those exotic materials that require higher temperature, for instance. And the remote and the control is via the Raspberry Pi, for instance. All of that, the patch is like 40 lines of code. It's not line of code, it's line of configuration. Just a configuration. So you can see in the shell there, it's just an header file that you change with, there are macros. Define this, just change that. 40 lines of code, really nothing. You recompile, you reflash, the machine supports what you just saw there fully. So that shows you it's really ready for improvements. It's really easy to use, really easy to hack. Quite nice. Okay, that was about 3D printing. Easy. Now, CNC. Second part. So CNC is a different world. So it's much less common. It's not that you don't find that everywhere. It's mostly industrial. You buy a machine for a huge price. The software costs you a lot. It costs you tens of thousands, and every year you need to pay extra and so on. It's really good, but it's not for amateur or do-it-yourself hackers. But no, you can do it. So I started from a machine, and I said, what would I do with this? So I noticed CNC is quite similar to CNC, because hardware is kind of the same. It's X, Y, Z, move ahead, right? It's put on, put off, measure maybe temperatures, things like that. But the core of the machine is the same stuff. It takes ahead, right? But it differs as well. The tools, they must be different. They are different. You cannot use regular tools to do CNC. Why? Because the slicer is not really, and it's not independent. You cannot write just the slicer alone, like for 3D printing. What you do in a CNC machine is, in fact, engraving a part in another part, subtracting one from the other. That's the main difference. So the slicer for 3D printing doesn't apply there. You need to do something different. So how do you do that? You need a CAD program that supports this, supports this principle. Remove a part from another part, given their constraints. The head moves, you interact with the model, you cannot bump into the model if you go too far, whatever. Also, the start reference point. So in 3D printing, the start is just the start of the bed where you print. In CNC, it's different. The start is on the part that you want to engrave. So you need to calibrate, put the head precisely at the 0 point, and then start going down. You would start, so basically you do 0 there, and you go negative in Z axis. While for 3D printing, you put a 0 and you go up. That's the main difference. So you need a software on the host that supports this. Okay? So rapid tour of host tools that I tried myself. I just tried a few of them. I'm sure there are others. Those are open source and they work, but more or less, right? PyCam, I tested first. It's a set of Python scripts and an application. You can see screenshots. It's basic, but it works. It does the job. Not many options. It's not maintained anymore. It's quite old. but it works. So as a start, it was fine. Then I tried Linux CNC distribution on a bigger board or Raspberry Pi. It works as well, but I found it really hard to use, and yeah, not really good. But it's a long time ago. Then I saw CNC Toolkit. I see guys using that. I never tried myself. I don't know. Then comes Freecad, latest release, really good for that, really nice. It works out of the box. There is a CAM module. So you use Freecad to model the part, to subtract a part from another, you get the result. Then you can instruct the CAM module to generate G-code to engrave this, right? So you can do profiling. Profiling is just get the outside detour of the part. So you can, like this part here in plexiglass, you can do the outside. That's the profiling. Then you can do drilling, yeah, holes. And then you can do engraving. So let's say I want to put the embedded recipe logo in this. I can just engrave ER embedded recipes in this board. That's engraving operation. So Freecad is highly configurable. You have a lot of options. You can do Python scripting. You will see it's really convenient in my case. It's mature, as I said. So reusable, stable, no problem there. So what about the machine? So a friend of mine gave me the machine for free. I was really happy to get it. Sorry, quite old, but looks like new. You know, it's German over-engineered stuff. Weighs 40 kilograms. You need alone. It's a bit heavy, but it's really good. Mechanically, it's really good. The power supply is just a monster. You know, toroidal transformer caps that big, really good, but firmware was really old, was running off non-standard stuff on the serial port or parallel port, I don't remember. Application was only on DOS, 6.2 something, okay. Works, I've seen it working, not bad, but it's not what I want. And I think now the application, you cannot find it anymore, you have to pay or whatever. I did not want that, so what I did is try to hack this to keep what is good in the machine and modify what I want. So here comes the tinkering. So leverage the hardware electronics, so the hardware of the machine, the power supply, I keep. And then I take the best of the 3D printing stuff. Here comes the 3D printing part that I explained before. I take the hardware and the firmware, I integrate this in the machine, and then I have a CNC machine. So how do I do that? I choose from a list of boards that are compatible. They are supported by the firmware Marlin. I choose for a Rambo board. Rambo should be robust, I guess. See, why? Because 24 volts, because it's the power supply I have. And Rambo stands for RepRap Arduino Marlin compatible board. Was just what I need. Then you have a USB interface to connect the laptop, to do the update, but also to send G-code if you need. And I've added a basic LCD buttons and SD card reader. You see the blue thing. On the left side, you see the SD card, this white stuff. It's the SD that you insert into it, and you can read from the SD. So yeah, I have the basic stuff. You can see more or less clean wiring. Give me a note after the talk. Just interface the stepper motors, the end stops, power supplies. Let's go. What about the firmware? Same as for 3D printing. 30 to 40 lines of config. Not a single change in the code, just configuration. So I needed to put my oscilloscope on the stepper motors, looked at the current, the phases, everything, timings. And from there, I derived the parameters to put in the configuration file, test it again, until it was okay. So just simple modification, a little bit of patience, you get it. I have, by the way, a GitHub repo in the reference if you need. So yeah. That was about the machine. So now about Freecad. So I choose Freecad because you can do everything you need just at just one place. So what do you do then? You can configure Freecad to have pre-amble code and post-amble code. Means G-code instructions you have to put before the print job and after. That allows you to set the starting point, 0, that I was talking about, to ask you via the button, are you okay, are you ready, is it configured correctly? You say, okay, you press the button, and it starts. Let the spindle start, so the machine runs, does its job, and at the end, you run the post-amble code to come back to home, to 0, put the spindle off for security, and so on. So that's basically what you need to configure in Freecad. It's mostly G-code, extra G-code, nothing. And then I realized the post-processor, so the Python code that exports the G-code was not compatible with my firmware. Stupid stuff like \n, happens. Some fast moves, because when you are not in the part, you are outside the part, you can move much faster to gain time. When you go in the part, you need to respect a speed, depending on the material. That kind of fixes. So what I did is to write a Marlin post.python script. So it's basically the one that is in Freecad. I copied over, changed, and put in a directory. It takes this one instead of the original one, and that's it. You can see on the picture default arguments. Then you can see the post-amble, pre-amble code, basically G codes. You see M300 and so on. You can do a beep at the end, basic stuff. So that's about Freecad. I will give a demo of Freecad if time allows. Should be fine. Something else, I did not try that, but I've seen it working. It's really cool. You can engrave the PCBs with Freecad. So there is a plugin, really magical. You import the KiCad design files in this. It draws you the board, all the layers, everything, and from there you generate the G-code to engrave and let the traces, only the trace you need. You can see the part in green. That's what the head will do. All the green stuff, the head will just remove this. And it will keep only the traces. Cool. Only for 2 layers. Otherwise, But yeah, really useful at home. You don't need to buy expensive stuff. You can do that if you need. That's about the CNC stuff. So conclusion, quite rapidly. Open source 3D printing, it's really doable. And my opinion is really the way to go. I don't see any other option. It's really mature, robust. You can do print farm, you can do whatever. It's really nice. Open source CNC, it's okay. Quality is more than okay. It's usable, it's mature. For small companies even, I find it really interesting because you have the freedom. You don't have to pay all the time. You are at home, you have your software. You do as you like. So I will try to give a demo now. So start from a basic sketch, do a part, and engrave in this part. Let's see. This one. Ooh. Nice. So this is a part, right? Supposed to be a keychain. So you see, there is a 3D part, basic block, and then try to engrave a hello stuff in there. That's the idea in 3D. So how do you do that? You start from a sketch. This is the sketch. It's a 2D stuff. You give dimension constraints, whatever. You draw in this. You can move stuff like. Whoop. You see, this one is not constrained, so I can move it. because the vertical line is constrained, so it keeps vertical, but the point there is no constraint, so I can move it. I could constrain it with a dimension on the right or an angle on the left, whatever, then it will stay like it is. A keychain requires a hole, right? I will put it there. You see, it's calculating stuff, because in the background, it's recalculated all the parts that the CNC needs to perform later. So I have my sketch now. I close it. You see, it has been updated automatically. That's what I was talking about, non-destructive geometry. You generate one part, then afterwards you change parameters, dimension, whatever, and it reflects directly in the part. And then I have the shape string is just the hello text. And this hello text, it's a shape in 2D, then I can extrude it to get, right, a 3D part. Then what I do is a Boolean operation, so I remove the hello text from this initial block. That's the cut. You see there's a cut. It's a Boolean operation. See, so 5 minutes, I'm okay. You remove basically the hello object from this one. That's the cut operation. Then, okay, the model is fine. What you do now is try to generate the CNC G-code from there. So you create a job. You see a job here? That's the job that will contain operations. The job has a lot of options. The tool you use, the speed, all of that. And then you create operations in there. So, for instance, profile, you see a profile? That's the one. You profile the part, so we just do the contour, and you see layer by layer, because you cannot engrave like 10 millimeters at a time. So you say, I want 1 millimeter at a time, depending on the material. It will do it 10 times. You see? That's the one. Then, remove this. You can do an engraving. So you see, start from this point, goes there, engrave this, and then back, and do all the letters. And I gave a finer pitch for the example. So you see all the layers. So it's just doing engraving of what is needed to be removed. Cool, huh? And from there, then we have the part that are generated. Now we'll export. So we go to job. You do post-process, and it generates the G-code. So you see the preamble, right? It does all the thing, change the tool if needed. Even if it's manual, you can change the tools in between. Does all the G-code. You see it's layer by layer. So you always go from 0Z to -Z. Does the whole thing, and then at the end, you see the post-amble. It will stop the spindle, go back home for security, beep, do something else, whatever, and that's done. So you get it. You save that. Save that, put it on a SD card, go to the machine, or upload via the Octoprint if you have it, and you can start. That's basically it. Right? It's easy. That's a simple demo, but really Freecad works really well, so you can do really bigger parts on a regular laptop, no problem. Then I have another case is where you need a more complex part. This is a part. This is a cargo bay for a small plane, RC controlled plane that we put below. It's a belly, like kind of. You can see it's made of different parts. So this is the shell that I remove, just for you to see. There is a plate in between, so you have two tanks of things you can put in. You have the doors at the back. You can operate them while flying to drop stuff. You have brackets. You have a lot of them. See, so it's a complex assembly of parts. And the message here is that some parts you just 3D print them, directly, like mechanism, brackets, you print them. So export the STL, go to the slicer, print them. And then there are parts like the flat parts you can see with the green. You can do CNC. See, this is a CNC G-code. So just to show you, Freecad can do it all. One assembly contains 3D and CNC parts, all in one tool. It's basically what I wanted to tell you. Let me see back here. So that's this example. Then if you want, there are a lot of references for you to see. My GitHub there, if you want to see the scripts, whatever. Right. Questions, remark? Do you use something else? You have suggestions? I'm there.
I built some of 3D printers by myself. Till now, no CNC. And major problem which I had till now was to make like it's embedded world scenarios, build a BSP with all needed components like Clipper, Open Print, Octoprint, and so on. So have you seen anything packaged like in Yocto or something like this to make life easier?
For the host tools, you mean, or to be the printer itself?
I mean, a BSP which should be used for the printer.
No, it's not really a BSP in that case. It's really just like Arduino kind of code you put in a project, you compile. It's rather basic, I would say, even if it's complicated. That's the way to go. Or go to Clipper or to Marlin. You will see a lot of on the GitHub. You will see a lot of README documentation, but it's really easy to use. I would say really easy to build.
Because for my in my experience, it was too loosey to all of these parts like Clipper configuration, Octoprint configuration. Everything is just pulled from each other. And just make a BSP which is concretely for this printer with all needed parts.
That's correct. It's 3D printing is a bit experimenting yourself, try error. Otherwise, you have a lot of money. You really nice machines. You see Vorum Design. It's a brand.
I built one of this.
You go to the website. You generate an SBOM. Yeah, it's really the BOM of material and of software. You add options, size, you click and you get the BOM. And then you buy the parts from there or from where you want. And the software is also configured correctly for the printer. That's really the luxury solution. It's really nice. But that's the high end of stuff. You can do it really yourself, no problem.
Thank you. On the market, we have a number of 3D printers that can be, let's say, converted to Marlin or similar, some low-cost stuff.
Yes.
For the CNC, we have something, or we have to resort to finding old hardware, let's say, and then hack on it to obtain something. And
there are also options. You can buy machines that are ready-made or in kit form. It's existing like, what was it? Mechanica.io, you see this reference? Yep. Then you can find kits that you buy. You buy and you build yourself in all sizes. It's quite easy. It's basically aluminum rods, stepper motors, belts, and so on that yet you assemble.
Thank you.
Can you, in the CNC setup, can you actually tilt the tool head somehow in the CNC machine, or is it fixed?
You mean to have a forward axis to?
Yeah, tilt the tool head so you can kind of mill underneath some sort of a top layer.
It's
Is that
also,
possible?
yeah, it's possible. I did not try it myself, but I know it's possible. I've seen some, what was it? I have this somewhere. In the CNC toolkit, you see?
Mhm.
This can do multi-axis. So there are tools to do this.
And
But
the CNC device which you have can do multi-axis then?
Of course, you need a machine with a 3D plus
Yep.
rotation of the head. And you need a special machine for that. Or
Thank you.
Arcade one.
Thank
Yeah.
you.
But I do only 3D myself. But why not later try something else?
Cool stuff, thanks.
Thank you. Over there? Koen had a question, no?
You should practice with chocolate.
We are in a basketball training session. Oh, nicely. Oh, missed.
Hard to catch.
Yes.
So my understanding is that you're reusing the firmware from the 3D printer and modifying the config to apply it on CNC machine, right?
Yes.
For a 3D printer, the task is quite easy and it's sufficient to use open loop, right?
Mm.
But I would say in the CNC, based on the material that you're using, there are like other elements such as forces that you need to take into account and heating of the part of the material, right?
Yeah. Correct.
How do you consider that for the CNC machine with these solutions or with this firmware, or are you even considering it?
Yes.
Considering that you are using the
Yes.
3D printer firmware?
Indeed, CNC in some material is really tricky. Like aluminum is really tricky. If you go too fast, it's kind of bouncing. It's like too stiff. If you go too low, it melts. It's a mess. It even breaks the milling tool because it melts around it. So you need to be careful about the speed and the rotation speed of the machine. And indeed, as you said, I'm using a 3D printing firmware to do CNC. You can see on the blue screen, there is 0 degree, that's the filament, because I'm not using it. 22 is the board. Yeah, the board in my lab is 22, but I don't care much. But yeah, for the speed, it's really important. So I have a sheet of per material I made testing. I broke a lot of bits, of course, because with aluminum or some plexiglass is better than other. Like the transparent is better than the white, for instance. The white melts a lot, while the transparent it makes it really clean. So I adapted the speed and the oiling also. You need to oil the stuff regularly, but it's manual for the moment.
So currently it's only open loop. There is no, let's say, capability of expanding and consider, for example, force sensors in the CNC.
No.
All right, thank you.
Yeah.
Okay, thank you, Jean.
Thank you.
Nice.
Thank you to BayLibre for this conference. Really nice.